Welcome back to Think Tech. I'm Jay Fidel, and it's 1 o'clock rock. It's Research in Manoa, which we do every Monday at 1 o'clock. We love that. One of our favorite shows of all time. Staying in touch with the scientists up there on the hill in Manoa. And our scientist today is Chris Peterson. He's the director of the, let's see if I get this right, the Pacific Regional Planetary Data, the manager of the Pacific Regional Planetary Data Center at HIGP, the Hawaii Institute of Geophysics and Planetology. And also you'll see he's the president of the Hawaiian Astronomical Society. Welcome to the show, Chris.
Thank you, glad to be here, Jay.
Great to have you. So let's talk about, the two things that are notable. One is a lot to do with these planets over here. But I think that's the Astronomical Society,
No,
or
it's
both?
It's both. These are from the data center.
Okay,
Brought them in
okay.
from the data center. So.
Data center. I mean, we have learned here on Research in Manoa that data, big data, is really important to everything SOWEST that HIGP does. In fact, every scientific organization on the campus has some connection, some need, some benefit out of big data. And you are a very important person to us because you can help us understand exactly what's going on with big data and with the data center in HIGP. So tell us what it is you do.
Okay, I think we should give a little historical background here to understand our situation. The NASA set up this group of organizations which they call RPIFs, that stands for Regional Planetary Image Facility. And just by the name, you can tell probably that they were set up long ago. In the early days of NASA's planetary missions, there weren't very many scientists and there weren't very many missions, and there wasn't very much data coming back. And it was all processed in the form of photographic images. The data may have come back in digital form sometimes, but it was still printed out as an image, flybys of the moon or Mars, and they would only send back, a few dozen or maybe a few hundred images. So in the early days, as I understand it, every what they call principal investigator, every main researcher that working on a project for NASA got a copy of everything. But as the number of missions grew and the number of scientists grew, that became financially untenable. And so they established this group of facilities called the Regional Planetary Image Facilities in order to have a central repository of the data where groups of scientists, planetary scientists, could view them and to save costs. So this program started in the 70s. Our facility began in the early 1980s, and NASA would send us copies of all the images from the Apollo program and beyond. And we would keep those, and also we keep books and journals and things that scientists use to do their research. So we were going along in this mode for many years. Then
Let
finally,
me ask you about the early days.
okay, sure.
So you're having the satellites, whatever, space vehicles are out there with these really terrific cameras, taking these beautiful pictures like the kind we see on NASA's website.
Yes.
And they all treat it as public domain, so you can
Yes.
pull it out and
Your
use it.
tax dollars pay for it, so it belongs to
It's
you.
great stuff. And this is with a fabulous camera up there in space. But then this image comes back to us live from space, as I understand it. You don't wait for the spaceship to get back. You get a radio signal, do you?
They're transmitted back.
Oh,
Usually they're
transmitted
stored
back.
on board the spacecraft and
Yeah.
then transmitted. It depends on the spacecraft that are far away, like the New Horizons mission that just flew past Pluto.
Yeah.
It's so far away, it takes time for the data to come back.
Yeah.
It's transmitted in a digital stream, but at the rate that is affordable with the equipment they have and the time they have available.
So this was like digital photography before digital photography was available in the consumer market.
Yes, I mean,
It's the original digital photography.
it started out analog, actually.
Really?
Some of it. Interestingly enough, some of the early lunar missions, the lunar orbiters, they had a Volkswagen bus-sized spacecraft that orbited the moon and had a photographic lab on board. And it took film pictures of the moon's surface, developed the film,
Like a
the
Polaroid
negatives
or
on
something.
board this
Yeah.
spacecraft,
Yeah.
then scanned line by line, sent back, I think, an analog signal that was received and then reconstructed, and then they made new images out of there. So the early days, it was even analog, even for space stuff. But pretty soon, it did turn digital. So just the ones and zeros come back in binary form,
Yeah.
and the images are reconstructed from that.
We don't realize that back when, they didn't have computers that are anything like the ones we have now.
No.
Even one personal computer, PC or Apple, up on those spaceships would have been hugely valuable, but they didn't have them.
A smartphone is far, far more powerful than the computers that landed the astronauts on the moon or that sent Voyager past
Amazing.
all the giant planets.
Okay, anyway, so going forward,
Okay, so
it changed.
then there was a transitional to digital data. For a while, we were getting CD-ROMs of digital data because the internet was not that fast yet, and not everybody had access to a good, fast connection. So we would have just banks and banks of CD-ROMs with digital data from the Galileo mission to Jupiter, for example, and beyond for a while. But it didn't take long for the internet to catch up. And so nowadays, people don't usually access data, the data, current data from the data center. That's not our role anymore because they just get it online. We do have all the archival material. We have lots of things such as these globes, maps, books, other documents that haven't all been digitized yet. A lot of things are being digitized, but they haven't all been digitized. And we contribute to that effort of digitizing things from time to time. But
that means scanning them?
Scanning them, mm-hmm.
That's a real project.
Yes, it is, and so that's why not all this old stuff has been. The most important stuff they're working on and getting done, but there's lots of things. We just recently had a request for some images that aren't widely available, Apollo 14 photographic index book that we have, and not all of the RPIFs have them because it dates way back. And so a lot of things we got from donations when people retire and, oh, they had this old material and they give it to us.
Yeah, I mean, is it fair to say, just looking at this as a trend, as a trajectory, that some materials that are in non-digital form, in graphic or analog form, will actually never be scanned? They'll just stay in the library because it's so difficult and expensive to go back and scan everything into digital form.
That's probably true. The things that don't seem to have a lot of value and nobody's asking about probably will remain unscanned for a long time anyway. I imagine eventually everything.
Just do it one
will
by
get
one,
done.
though,
Yes.
on demand.
Well, there are projects. There are projects that NASA pays for certain things, and of course the primary data from missions like the images that the astronauts took with their Hasselblad cameras or from orbit that are analog still. Those things, there's projects to digitize those, and they've kind of waited until the scanners were good enough and they could get all the digital quality out. It takes about 20 megapixels to equal the slow in detail. And so it's only, fairly recently that scanners have been able to really get all the detail out. And there's no point in doing it if you're going to have to redo it again in a few years. So.
The other thing I was going to ask you is what are these globes?
Okay, this is some of what we have in the data center. That's non-digital.
Okay.
There are reasons to have some things that are not digital. These are globes of the terrestrial planets. The terrestrial planets, that means the Earth-like planets. And these are the planets that have a solid body. You could walk on them. They usually have at least some atmosphere, although not much in many cases. But these are the terrestrial planets. This is Mercury. Mercury, at the time that this globe was made, had only had one spacecraft go around it. So we didn't even know what the other side looked like. We do now. We have a much better globe. But these globes are all to the same scale. These are the same size. This is our familiar Earth we all know and love. And this is how big Mercury is compared to Earth. This one is Venus. Venus is sometimes called the twin of Earth. It's just a little bit smaller. This is actually a little bit too big. This globe is not exactly to the same scale. It's should be just a little bit smaller than this, but you can see it's a little smaller. But Venus is covered with clouds, and you can't see the surface. So radar was used to get this, and this shows just the topography of Venus. It's not, the blue is not water. It's much too hot for water. Lead would melt at the surface of Venus.
So that's the scale. So that Venus and the Earth are about
almost the same size.
Isn't that interesting?
Mm-hmm. Yes.
Didn't know that.
And surprising to many people, well, that's Earth, and this is the Moon. Moon is only 1/4 of the diameter of Earth. And so...
if you look in the sky, it doesn't look very big at all.
Yeah, well, it's...
that's bigger than I thought,
That's the size.
actually.
And here's Mars. This is surprising to people. It's only about half the diameter of Earth.
Mm-hmm.
Because you look in a book, and all the planets are round, and they take the size of a page, right? So it's really hard to get an idea until you compare them with each other. And so that's a helpful comparison. But there's not only size you have to compare, but you have to compare distance. And so I usually do this demonstration at the university in the data center at Manoa. And at that scale, if this is to the same scale, the sun would be the size of a 13-story building at the foot of New Wanu Street in Chinatown here. And between there and UH, you would only have Mercury and Venus, and then you're at Earth. Mars would be about at Hanauma Bay, and Pluto would be on the Big Island somewhere. And Pluto is only about 2/3 the diameter of our moon. So you can understand how hard it is to see Pluto. Try to think of seeing this on the Big Island with your naked eye. It's very difficult.
Yeah.
So that's how hard it is to see Pluto in the
These
sky.
are little tiny fragments when you compare, to a 13-story building.
Right, right.
Wow.
And that's just a very small scale in the universe. When we get to bigger distances, we have to talk about the time that it takes light to travel, because miles just get to be too big numbers to understand.
Yeah.
So light travels at 186,000 miles per second, or 300,000 kilometers per second. So it takes from the sun to the Earth takes about 8.5 minutes for sunlight to arrive. The outer planets, it takes hours. The nearest star to Earth, Proxima Centauri, it takes over 4 years for light to travel that distance. Our galaxy, the Milky Way, it takes light 100,000 years to travel across. And then from the moon to the Earth, about 1 1/3 seconds.
You think we'll ever get to these faraway places?
Well, it'll be difficult to get to very distant places, but we will certainly populate our other places in our solar system within a few generations. We're capable already of going to the moon. We did it, and we could have been going there regularly had we not invested in the space shuttle instead. Had we kept flying the Saturn V rockets, for example, we could have gone to the moon once or twice a year for the same money pretty much that we spent on the shuttle program. And so we could, by this time, we could have a permanent settlement there on the moon. So we'll get around to that. Mars is a little more difficult. It takes only 3.5 days to get to the moon with current technology, but it takes at least 6 months to get to Mars. And you're talking about probably a 1.5 year round trip because you can't come back right away.
Yeah, when we come back from this break, though, I want to ask you about the movie, see what you think.
Okay.
Yeah. That's Chris Peterson. He's the manager of Pacific Region Planetary Data Center at HIGP. He's also the president of the Hawaii Astronomical Society, and there is a direct relation between these two things. Here in Research in Manoa, we're talking about come to our star party. Join our star party. But right now, let's join our break.
Hi, I'm Donna Blanchard. I'm the host of Center Stage here on Think Tech. This show is so very dear to my heart. We talk with artists of various different ilk here about the process that they go through for their art. So we talk about what they're doing, why they're doing it, how they do it. And it's a show that is inspiring. This is what I hear from people all the time. And a show that will teach you something, sometimes something about yourself. I hope you'll join us. The show is Center Stage. It's on Think Tech every Wednesday at 2 o'clock. We'll see you then.
Aloha, my name is Josh Green. I'm a senator from the Big Island in the ER position. Every other Tuesday, I get to host a show here on the Think Tech program about healthcare. We call it Healthcare in Hawaii. It's really enjoyable for me to bring other healthcare leaders from around the state to talk about our pressing issues. Hawaii has long been the health state, but we need to keep up the momentum, the inertia, and with your help and with your participation, we can come and share all of the big issues that are pressing day to day. Thanks for joining us every Tuesday, alternating weeks from 2 to 2:45.
We're back, we're live. We're here with Chris Peterson of HIGP. He's the manager of the Pacific Region Planetary Data Center. We'll be talking about that more in a minute. But I just want to get your take on what you've heard about the Mars movie. I mean, where does that fit in this notion that we were just discussing about how we're going to get out there and we're going to be walking on these planets?
Well, we know that it would be possible for people to visit Mars. There are some things that were a little bit misleading about the movie, I've heard. For example, there are strong winds on Mars. There are windstorms on Mars that create global dust storms, but the atmosphere is very thin. It's only about 0.5% of the pressure of the Earth's atmosphere.
Wow.
So even a 300-mile-an-hour wind wouldn't knock you over and wouldn't, throw things around like it did in the movie. But I've heard that much of the movie was much more accurate than most Hollywood movie representations of space are.
Yeah.
You can't expect, it's not a documentary, it's for entertainment, but people will need to be protected no matter where they go. The moon, Mars, there's radiation coming from the sun, coming from the cosmos, there's galactic rays that will kill you if you're not protected. And so, not right away, just the daily exposure is not enough to kill you right away, but things like solar flares could. If you're out and the solar flare sends radiation towards you, you have to be protected. So there has to be some sort of habitat, either underground or with some sort of protection above ground to protect you from radiation. There's a place on the moon that would be very good for this, or several places. One of them is the Aristarchus Plateau. It's easy to notice because there's all this dark area. The dark area on the moon is lava that erupted many years ago. It doesn't look dark here, but the smoother areas. And the highlands crust is lighter. So in this dark area, there is a very bright crater that's on the edge of a plateau where there were pyroclastic eruptions, just like we have on the Big Island. We have a fire fountain volcano. And because the moon has no atmosphere and lower gravity, then these particles broke into very fine pieces and took a long time to land, and so they solidified before they hit the ground and built up a layer several feet thick of this very fine talcum powder-like pyroclastic ash, which is very useful to use for many purposes, one of which is shielding. You can dig it out very easily, put a habitation module down and cover it over with this stuff, and several feet of it is enough to protect you from the radiation. There are also lava tubes on the moon and Mars that might be suitable to be retrofitted into a habitat where you already have material above ground to protect you from the radiation. But to be walking around on the surface just all the time like that is dangerous to your health.
People should know about this. The aspiration of going into space, going to other planets, it's reaching for the stars, and that means we live a more philosophical life, questioning exactly what is this all about. I think it's better that we do that than get involved in wars and all those things.
No, I agree with you there, and that's a big part of what we do with the Astronomical Society. I haven't really talked about that hat I'm metaphorically wearing also today, but we conduct what we call star parties, public observing sessions every month. We do a couple in town when the moon is in the sky, and then out at Dillingham Airfield when the moon is not in the sky, so we can get the darker skies. You don't really need the dark skies to see the moon and the planets because they're pretty bright.
Yeah, while we're on it, so how do I join the star party with the Astronomical Society?
Well, we have a website. Use the first three letters of the three words in the name, haastsoc.org.
Okay.
Or you can just Google Hawaiian Astronomy. It'll come up there.
Yeah.
And So
Can anybody come, or do I have to be a scientist?
you don't have to be a scientist. You don't even have to be a member to come to our meetings. We meet on the first Tuesday of every month at the Bishop Museum Planetarium. Usually, sometimes there's something going on. We're somewhere else in Bishop Museum. But it's at 7:30 on the first Tuesday of every month. And we sometimes have an outside speaker. We usually use the planetarium. One of our members is someone who runs the planetarium shows, and so she shows off what's going on in the sky tonight or some other program that they may have. And we talk about what's coming up. We do a lot of service projects. These star parties, we do the regular public star parties, and also we do star parties for schools or other organizations that contact us and would like us to come out. We'll do that also.
I was telling you when we spoke on the phone, there's seems to me there's huge interest in astronomy in this community. I mean, you can tell by going to the IFA annual open house, Institute for Astronomy on Woodlawn Drive, that people from all walks of life are fascinated with astronomy. And it's a big hobby. They care about it intensely. They have telescopes that are not cheap. And they come to every gathering they can find to learn more.
Mm-hmm. Space and dinosaurs are what's most popular
Really?
for kids, in the early elementary grades. And so we try to get them when they're young and get them hooked and get them interested and see that it's something that they can do.
Yeah.
I'm always surprised when we have these star parties. It seems like a large percentage of the people who come to each of these star parties, they have never looked through a telescope in their life at anything. And so to see the moon, to see a planet, it just blows their mind. And things that, like I was talking about earlier, with its size and the distance scale of the universe, it expands your mind. And we spend so much time these days looking at something in our hand, we don't even look up and see what's around us.
We need to do that.
And that's just our planet, let alone what's way out there. And we're just such a tiny little speck in the universe that I really think it's helpful and useful to help people explore this kind of idea.
Yeah, and even if it's exploration through a telescope, even if you're never going to get on a mission to go there, it enhances your view of the universe. It gives you greater depth in appreciating the universe, and that means science. So when these kids go out in high school, and study planetary issues, they're getting close to science, and they're likely to be drawn into science for a career, which is a great thing. So it's worth educating them. It's worth having an astronomical society.
Yeah,
I remember one kid he was a junior at Iolani School. He was in the science, the science fair, and he actually discovered an exoplanet himself, personally. In all the world, with all the astronomers and scientists, this kid, I think he might have been 14 or 15 years old, discovered an exoplanet at Iolani here in Hawaii.
I think we gave him awards, both the data center and the Astronomical Society. I think gave him awards at the science fair that year.
Lindsay was his name. Christopher Lindsay.
Right, yeah.
Your namesake.
Right, yes, I remember him. And but observation, as you mentioned, that's really the beginning of science. Science all starts with observation and with data. Brings us back to data. That's the root, and then you have to use that. You have to look at it systematically. Slice it and dice it, look at it, arrange it, figure out what it means, and that's what doing science is. But you don't have any science without data, without observation, and so that's the common ground between astronomy and the data center.
So when we talk about the Pacific Region Planetary Data Center, we're talking about lots of graphics, I guess. We're talking about Pacific Region.
We serve the Pacific region. These are designed, these regional planetary image facilities, the generic name, were designed to service a particular location and the people in the surrounding areas who needed to come and look at these. And as I've said, our focus is changing. We have in the past cooperated with universities in Guam and things like that, sending them materials. NASA used to send us a lot more posters and things like that than they do anymore. But we're moving into a new era now, and so we're starting to adjust how we handle data. One of the things I'm trying to work on is to create a website that brings together all of the sources of planetary science data, digital data, and all the tools for using it. Because having the data is one thing, but being able to do anything with it is another. And where we're not experts in all these programs and how to use them all, we do have an awareness of what's out there, and we can always learn more, and there's always new programs being developed for using things.
Well, I heard you talk about scanning, and that's a tool, but what other tools are you talking about?
Well, there's many programs that you can make measurements on images, or you can take two different wavelengths and compare them, take a ratio. Work I did for my PhD on the moon, I was looking at ratios of wavelengths that showed whether there was iron or how much iron there was in the soil to determine how much of the original crust of the moon was left, things like that.
This is from light? Or
Yes, just from reflected light, reflected sunlight.
Spectrum.
Spectral, yeah, spectral.
analysis.
We measured the return of the light in many different wavelengths. And then there are a few different wavelengths that are very important for particular lunar minerals. They absorb certain wavelengths of light. So if you ratio those wavelengths, you can get information. And the same thing is true on Mars or any other body. The minerals that are there react differently, but the same techniques apply.
Well, I'm getting pretty excited about this because, you know, you have this huge library, data center full of images going way back, and now you have tools that can do very sophisticated analysis. And every time you turn around, there's another tool that can give you an even more sophisticated analysis. So the old data can be evaluated in a more and more sophisticated way.
Yes, it's just very similar to the way that astronauts brought back samples of the moon from Apollo, and those samples were analyzed using the techniques that were available at the time. But now techniques have improved. There's things that we can do that we couldn't do, and so those old samples are being reused today, analyzed with techniques that weren't available when they were brought back.
Yeah.
The same kind of thing is true, for example, the old images of Mercury that were taken back in 1974 and 75 were analyzed at the time, and then one of the graduate students at HIGP, before it was HIGP, Mark Robinson, went back and looked at them and reworked them with some newer software, because they really didn't have many computers back then to do this. He was able to do more sophisticated work and learn more about Mercury using that old data.
That's very exciting. And but what it does say is that you really have to keep this stuff, because this stuff can be useful in ways you can't even imagine right now.
That's right.
You know? But right now we're going to take a short break. That's Chris Peterson. He's the director of the manager of the Pacific Regional Planetary Data Center, which is part of HIGP, Hawaiian Institute of Geophysics and Planetology, which is part of SOEST, the School of Ocean and Earth Science and Technology at UH Manoa. And he's also the president of the Hawaiian Astronomical Society. Here on Research in Manoa, we're talking about joining our star party in so many ways. We'll be right back.
Aloha, I'm Keli'i Akina with the Grassroot Institute of Hawaii, and one of our delights is to be partnered with Think Tech Hawaii and produce programs every week. Every Monday at 2 o'clock, we have a show called E Hana Kako, which means let's work together. So we bring people from all across the nation and the country, and certainly throughout the islands, together here to talk with them about how to work together, and how to work together to do the following: to build a better economy, a better government, a better society. So if you're interested in the research of our think tank, the Grassroot Institute, or if you're interested in how that's applied at the governmental and community and business levels, you'll enjoy the fascinating conversations with our guests on E Hana Kako every week on Think Tech Hawaii at 2 o'clock on Mondays. Until our next show, I'll see you. Aloha.
Okay, we're back. We're live. We're here with Chris Peterson, of HIGP, manager of the Pacific Region Planetary Data Center, among other things. And we want to know more about exactly how it works over there. So you have the data you got from space, you're processing it, you're learning more about what it shows. Where does that all go? Who uses it? Who do you send it to? Who is it available? Can I just look at it myself?
You can.
Can the kid at Iolani School, can he look at it?
There are ways to look at a lot of the data. There are places that just have pretty pictures, NASA Photojournal, among others. There are many repositories for the data, but there's a central place where people go to get this data. People that gather the data usually have access to it first for an exclusive period of time. If you're on a spacecraft mission, then you get the data first. And the data...
They have priority.
Yeah, the data generally has to be processed before it's usable. The raw data comes down and there's calibration. Anybody who's done any astrophotography knows about that these days. It's
What is
pretty common.
calibration?
There's certain artifacts in the instrument itself. There are hot pixels that have to be removed, or there's a gradient of brightness across the lens or something. And there are ways to remove this. You take an image with a shutter closed, and you look for the dark current in the. There's various processing.
But you
things.
expect this. I mean, this is the way it works because there are electromagnetic waves and the like going all through space. And
Yeah, no instrument is perfect. They've all got flaws, and so you have to
Yeah.
remove those. And there's techniques that people do,
Yeah.
and so that's kind of going from level 0 to level 1 data
Okay.
after it's been calibrated. But then the calibrated data is used for a certain period of time by the people on the mission. For example, there's a mission at the moon now called Lunar Reconnaissance Orbiter, and it's going around the moon. It has several instruments, but the camera, there are two cameras. It has a wide-angle camera and a narrow-angle camera. The wide-angle camera it takes images with about 100 meters per pixel. The narrow-angle camera, it's only a half meter per pixel. This table would show up as about 3 pixels on that camera. And so the data is gathered, and then it's looked at, and if there's something interesting, then somebody will look more at it and try and figure out what that means. And then after
are
a
the
few...
images put together? Are they
That's
consolidated?
part of the
in some way?
processing. It's part of the processing.
So you get a better image with both cameras that way. And
Yeah, you take the whole moon pretty quickly with 100 meters per pixel. They're still working on gathering the whole.
Okay.
And you have different lighting angles that reveal different things. The shadows are longer here or shorter here.
yeah.
And you can get stereo from looking at different angles. And so there's a lot of, you don't just take one snapshot and you're done.
So depending on what I'm researching, what I'm looking for, the kind of analysis I want to make about who knows what, about chemical composition, who knows what, heat, light, whatever, I might ask you for this kind of picture instead of that kind of picture.
Mm-hmm.
And I might not have the picture I need. Maybe I'll ask you to see if you can find a picture.
Right, that's the
with
kind of
data that I want.
liaison we can be. We can help you figure out where to go. And that's part of the purpose of this website I'm developing, is to bring all that together so that people can just go to the website and see where the data is available and what are the tools. There's many, many tools. For example, there's one, unfortunately, named ISIS. They'll probably be changing that soon.
I hope they change that soon.
It stands for Integrated Software for Imaging Spectrometers. It's had different names in the past. They'll probably change it again. But there are a number of routines that are common where you want to say, join these two images or several images into one big mosaic. And you want to calibrate them, adjust for, the lighting was a little different here than here, make it a standard lighting and show what it would look like if the sun were in the same position at all points, things like that.
Are you going to be able to help me with that? Are you going to be able to process it for me at my request, my instruction?
I could do some of that, but that's not mostly what we do. Most people who are in the business, they already know the program for what they're doing. But if someone comes from the outside and just wants to look at an image, not a scientist, but is a member of the public who wants to see, or play around a little bit, then we'll be able to guide them to some of the programs where you can do some simpler things like, oh, you can draw a line across this crater and measure the diameter this way and this way, see if it's round or if it's elongated, and figure out the depth of it, you know, how you can overlay topography on top of the image, things like that.
But the cutting edge guys are going to have their own tools, and they get the data of the photograph from you, and they take it back to their tools, and they work their tools on it. Is that what happens?
Well, generally they know what they're doing. People who are in this business, they've been doing it a long time, and most people don't write their own programs. There's these standardized programs that are out there, but there's many, 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 and they depend on the kind of information you're looking for. As you say, if you're looking for chemical information, are you looking for topography, are you looking for structural features, you might want to be doing things. Structural geologists would perhaps draw lines along faults and then look at the angles and the lengths and compare those and make a table of the numbers and all those things and compare one thing to another. Whereas somebody who's looking for the geologic history of the chemical evolution of the elements would look at different wavelengths and compare those to see what wavelengths of light are being absorbed to identify olivine or pyroxene or other minerals.
I can see why the guys working, for example, on the Mars trip coming up, they would want, and you would want to give them priority on these graphics so that they could study the place as much as possible, know everything about it before they go. Yeah.
Yeah, well, I mean, that's where the beauty of the internet is. There's no limit on how many people are looking at the same data and how long they want to use it, because it's all there.
Yeah.
And they can get to it any time and any place. So that's why our role is changing and how, and we're still adapting. NASA is undergoing a reorganization, and so there's some discussion now of what our role is going to be in the future. Up until now, NASA has not changed our mandate. The original mandate that we had to store all these images and share them with people and do public outreach like I'm doing now, that really hasn't changed since the beginning. And so we're looking now to how we're going to restructure our mandate for how we're going to deal with this. And I hope this website I'm trying to create will be part of that.
But your data will always be valuable for anybody doing this kind of research.
Sure, yeah.
Or the science, and you know, even going forward, you know, all your data will still be useful to somebody who's doing this research wherever in the world and for whatever project. So if you were NASA, Chris, what would you do with the data center?
Well, I would do what I'm trying to do, which is to use the resource of all the data centers to create an interactive website where people can go and find all. And this would go from anybody from just a casually interested person to the research scientist would be able to go find out where all the different kinds of data live, how to access it, and where are the tools, and where you go to learn how to use these tools. Some tools are easy and intuitive, others take really years of study. If you're going to really be good at this processing, you have to know what the tools are, what the individual modules are, how to apply them, when you've made a mistake, when you have to do it over. All those kinds of things take years of study to really become proficient at. So there's a whole range there, but we should be the interface from anybody who wants data and wants to use it for where to find it, how to use it, or how to learn how to use it.
Including NASA, or how does it work? I mean, you give it to NASA, does NASA give the data to you, or do you both give data to each other?
Well, no, it's we don't generate too much data. I mean, there's always some data generated from local scientists, but NASA mostly works with the spacecraft missions that are out there, and so there's a central repository for that data, and it's accessible to scientists. Generally, the way it works in NASA is a scientist will write a proposal. This could be a 1 year or a 3 year proposal to do a certain kind of research using certain data, but they're able to use whatever data is out there. They have a goal. I'm going to study the structure of volcanoes in this part of Mars, and map all the fault lines on them or something like that. And so then they go and they use the data that's going to be useful for them, and there's many, many Mars missions in the past and ongoing. So they need to know where that is and where to go find it.
So NASA has its
How do you
own
say?
data center. Is that fair to say?
Well, it's not a central data center, but there is a place where the data is sort of archived. There's a few different places where it's archived, but people know where that is and how to get that if they're scientists.
What about you? I mean, you're the Pacific Region Planetary Data Center. Is there another one for the Atlantic region?
Well, they all have their own names. That's just the name that
Yeah.
we chose, but it was sort of taken from the Northeast Regional Planetary Data Center in Brown. That's where our founding director went to school, and so well, that sounded like a good name. He just applied it here.
Okay.
But there are data centers, or RPIFs to be more formal, in Arizona and in Texas and at the Smithsonian Institution in Washington, Cornell University. There's several of
How
them.
about overseas in other countries?
There are in other countries. They never were funded by NASA. They never were sent the kinds of things. They may have been sent some of the data sets, but they never were funded like we are. But they're affiliated, and so it's part of the network. And so if someone comes with a question to me, but they live in Washington, D.C., I would send them to the Smithsonian and say, those guys are right there. They'll be able to answer your question in person and be more helpful to you.
So you say it's a network, and this really interests me because I've come to find that, science in the 21st century is all about collaboration and sharing and whatnot, and really altruistic sharing a lot of the time across all kinds of boundaries. So how does it work for one data center, your data center, to deal with the data center in Brown or in Arizona or in the Smithsonian? What do you do? Do you pass data back and forth? Do you talk to each other? You have conferences?
We do have
They come around
We do have
sometimes?
meeting. We have a meeting just about once a year. We have a meeting and to discuss how things are going and all that stuff. We'll have communications back and forth. People will ask about availability of. Now these days it's not the digital data because that's all online, but old.
It hasn't been digitized.
Yeah,
yet.
old undigitized data, books, documents, that kind of thing, and not all the RPIFs have them. Some won't, so they'll put out a request. Oh, does anybody have this or that, or particular images that haven't been digitized, things like that, and then we can scan them and send them on.
So if I'm one of the researchers that you serve and provide support for, where am I likely to publish? What kind of article am I likely to publish? What kind of conclusions am I looking for?
Oh well, there are many journals. The Journal of Geophysical Research, Planets is one of them. There's Icarus. There's many scientific journals, and these are peer reviewed. So you do your research, you write your article, and then you send it to the review panel. And there's a panel that will look at this, people who know that kind of work that you do, and generally they send back some criticism. Oh, this doesn't really support it. We need to talk more about this, or we disagree with this conclusion. And then it'll come back and you have a chance to revise and send it back in. And if the editor thinks you've done a good enough job, it'll be published. If you might send it back out for further review or just reject it entirely. But that's the way science works. It's not just an opinion piece. It's a piece of work that's reviewed by people who know what they're talking about and know if you know what you're talking about. And if you pass that muster, then it's published in the journal and it becomes available for people to use and to cite in their references and build on.
Is this process are you involved in this process?
Well,
Are
I
you
used to be when I was
writing or peer reviewing or?
When I was a grad student, I did research and wrote papers, but now this is an administrative post, so I'm not really doing that anymore. But I try to keep up with the broad literature on the moon in particular. That was my subject.
This is a feather in HIGB's cap because there aren't that many of them around.
Right. There's 9 in the U.S. and 8 others around the
Yeah, so
the
you're
world.
one of them.
Yes.
Well, I'd like to follow you on going forward. I hope the NASA story goes well, and the center is around and robust. And I wonder, if there'll be more of them in the future or less. What do you think?
I don't know. There probably will be. There are other people that have applied. I think Canada is applying for another one. There's one there already. So there may be more, but this is a subject that's not really certain yet. Where NASA's sort of reviewing all the facilities programs right now, and so probably in another year or two we'll know more.
Okay, we'll have to talk to you again. Chris Peterson, he's the manager of the Pacific Region Planetary Data Center, and also, if you hadn't noticed, with all these planets, he's the president of the Hawaii Astronomical Society. Thank you so much, Chris.
Come see one of our star parties.
All right, yes, join our star party. Thank you so much.
Thank you, Jay.
We have the website on the screen.
Great.
Good work.
Okay.